Keen, don't do that. All right. So next unit, chapters 8 and 9. We're going to use a lot of the stuff that we used in the previous chapters, especially dealing with the graphs of lines. That's what this unit is based on. It's based on systems of equations, which we're going to see is where you're going to have two lines together in a group. Keen. You're going to have two lines together in a group, and we're going to solve the system of equations. And we're going to see there's two different ways that this can be done. It can be done graphically, and it can be done algebraically. So we'll learn about both of these ways to solve a system of equations. But first, we got to know what it means to solve a system of equations. Some of the key terms we'll talk about the point of intersection, a system of linear equations, the solution to a system of linear equations, and what are known as coincident lines. So we're going to start in this chapter by looking at solving a system of equations, find the solutions graphically. So we'll start this off by looking at this investigation. How can you compare and analyze cell phone plan options? Plan A costs 30 cents a minute, where Plan B has a one-time cost of $15 plus 10 cents per minute. So for Plan A, it's straight 30 cents a minute. So if we fill in this table of values, for 0 minutes, that'll cost $0. To find the cost for 25 minutes, it'll be 25 times 0.3, which is 30 cents. So that'll be $7.50. For 50 minutes, it'll be 50 times 0.3, which is $15. For 75 minutes, it'll be 75 times 0.3, which will be $22.50. This is a linear relation, okay, because the rate of change is a constant, 30 cents every minute. There's a pattern here. As the number of minutes increases by 25 minutes, we see that the cost increased by $7.50. For 100 minutes, it's 100 times 0.3, which would be $30. And let's graph this. So the first point will be the point 0, 0. The second point is 25, 750, which is halfway between $5 and $10. Remember that the first number in a table of values always goes along the bottom. Brock, put your phone away, please. And that is n, the number of minutes. Where along the side, we're going to have c, or c at n. That's our function notation, that the cost is a function of n, the number of minutes. This is our cost in dollars. Remember that every graph needs to be labeled. So the next point we'll have is the point 50, 15. 75, 22.50, which is halfway between 20 and 25. And then 100, 30. So there's our last point. Brock. Can you put that away now, please? Thank you. Okay, so there's that linear pattern. And technically, we probably shouldn't draw a line through these points because that would tell us that there's a cost for half a minute or a quarter of a minute. And that's probably not true. So we'll just leave it as a series of points. Now, Plan B, a one-time cost of $15, which means you pay $15 every month at least, no matter what, and then an extra 10 cents per minute. So for this plan, even if there's no minutes used, it's still going to cost $15. And then for 25 minutes, it's your $15 base fee plus 25 times 0.10 for 10 cents a minute. So that'll be 15 plus 250, which is 1750. For 50 minutes, again, it's 15 plus 50 times 0.10, which will be 15 plus 5, or $20. And there's a pattern here as well. Again, the cost is going up at a constant rate of 10 cents per minute. That would be the slope of this line. It's the rate of change. We see that as the number of minutes increases by 25, the cost actually increased by only $2.50. So for 75 minutes, it'll be $22.50. And for 100 minutes, it'll be $25 if we continue the pattern. So if we put these points, we start at 0,15. The next point is 25,1750, which again is halfway between 15 and 20. The next point is 50,20, that point right there. The next point is 75,2250. So that shares the point with the previous graph. And the last point is 100, $25. So there's that graph. And again, we shouldn't join the points because that would tell us that it's possible to have a charge for half of a minute. Shane, you want to come and grab one of these? Which we're not told that there is a charge for part of a minute. So just by looking at these graphs, we can make some inferences if you want. So from the graph, explain the cost of each plan as the number of minutes increases. So you can see that the first plan starts at 0, and we know that it increases by, 30 cents a minute. The second plan starts at 15 and only increases by 10 cents a minute. All right? So that's basically explaining the cost of each plan as a number of minutes increase. They both increase at a constant rate. They just start at different points, and the rate is different. So if we're going to write an explanation, maybe that's what we write. They both rise at a constant rate. However, the two rates are different. Right? One is 25 cents a minute, the other is 10 cents a minute. The other thing that is different about them, one graph starts at 0. We'll say the point 0, 0, and the other at the point 0, 15. So there are some similarities. They both follow a linear pattern. They have a constant rate of change. The rates are different though, and they also start at different points. Now, part 4 asks, what is the significance of the point of intersection of the lines? Explain the connection between this point and the table of values that we created. So what's significant about these 2 points where the 2 graphs intersect? So that is this point right here. The point of intersection is the point 75, 2250. That is our point of intersection, where the 2 graphs intersect. So again, that's the point 75, 2250. Remember that when we set up our graph, The first number, which was n, was the x value. The second number, c, was the y value. So that point is where the n and c values are the same. And how we interpret that, this is the point where the cost is the same for both plans. That's what that tells us. Both plans have the same cost of $22.50 at 75 minutes. That is what is significant about the point of intersection. The two plans have an equal cost of $22.50, and that is at 75 minutes. So that's one use of this graph. It tells you where the two things are equal. The other thing the graph can be used for is determining what the best plan would be. You see, it would depend on how many minutes a person uses their phone. If you use your phone for less than 75 minutes, then plan A is better because that graph is below the other graph. That means the costs are lower. But if you use a plan for more than 75 minutes, then the second plan is better because after 75 minutes, that second graph goes below the first, which means the costs are lower after 75 minutes for the second plan. So this is what we can use that graph for, to determine which is the best plan. So which cell phone plan is a better option? If you use less than 75 minutes, plan A is best. But if you normally use more than 75 minutes, plan B would be best. The graph tells us that. Where the costs are higher, the graph is higher. Where the cost is lower, the graph is lower. So where one graph is below the other, that means the costs are lower. When one graph is higher than the other, that means the costs are higher. So this is one practical use of the graph for this scenario. So this is what we're going to be doing. Part of in this chapter is graphing lines. And we're going to see where the two graphs intersect, because they tell us some information about the scenario that we're graphing. So on the next page, it says, graph those two lines on the same grid below, then determine the coordinates of the point of intersection. These two lines are in slope-intercept form. Remember, that's y equals mx plus b. They're both in that form. So for the first line, m the slope is a half, and b the y-intercept is -1. And that's where we start, remember. We start with the y-intercept at -1. And then our slope is a half, so we rise 1, run 2. Rise 1, run 2. Rise 1, run 2. Rise 1, run 2. We can also rise -1 and run -2. Rise -1 and run -2. All those points line up. Right, so there's that line. Easy to do because it is in slope-intercept form already. Same thing with the second line. It's also in slope-intercept form. This line has a slope of -3/4, and the b value, the y-intercept, is +4, which is where we start. Y-intercept of +4. Our slope is -3/4. So rise -3, run 4. Rise -3, run 4. We don't really have room to rise +3. We'd have to kind of estimate where that takes us. And then if we run -4, it'll be over here somewhere. And that point appears to line up with all the other ones. So that's good. We can draw our line going through those points. And we want to get the point of intersection where the two graphs intersect. And that appears that is the point 4, 1. That is the point of intersection of these graphs. Because the slopes are different, there is a point of intersection. Remember that if the slopes are negative reciprocals, we learned last chapter, that means that the lines intersect at 90 degrees. But they still intersect. Whenever the slopes are different, the two lines will cross somewhere, and that is the point of intersection. So we'll do the same thing for these two equations. Once again, they are in slope-intercept form. Y equals mx plus b. M, the number in front of x, is the slope. B, the y-intercept, is the constant. This one has a y-intercept of -5 and your slope of 1. And remember, slope was always rise over run, so we would write 2 over 1. Rise 2, run 1. Rise 2, run 1. And we can do that multiple times. All those points line up. And there's that line. The second line is also in slope-intercept form. M, the slope, is 1. There is no number in front of the x, but there is 1x. So the slope is 1. B, our y-intercept, is -3, and that's where we start. Y-intercept of -3. Our slope is 1, which is 1 over 1. We rise 1 and run 1. Again, the slopes are different, so the two lines do intersect. And we want to state what that point of intersection is. And that is the point 2, -1. That is the point of intersection. The point 2, -1. And so for these first two examples, right, the point of intersection, each x and y value were integers. So from the graph, as long as you draw it carefully, you'll get what those points of intersections are. We will see some examples where the points of intersections involve fractions or decimals. And that's where we're going to start looking at the algebraic way of solving these, using algebra. But for now, we're doing it graphically. And so our answers, I think, will all be numbers involving integers. So a system of linear equations is where you have two or more equations involving common variables. A system of linear equations is often referred to as a linear system. It can be represented graphically in order to make comparisons or solve problems. The point of intersection of the two lines on a graph represents the solution to the system of equations. So that's what we found in those last two examples. And then the one before that dealing with the cell phone plans. When you find the point of intersection, you are finding the solution to the system of equations. The solution is the point of intersection. Okay? You need to write your test you missed yesterday, so you got a pen or pencil? Yes, no? Okay, borrow a pencil off my desk. And grab a calculator. off my counter there and come with me, please. So the point of intersection is the solution to a system of equations. So in the investigation we just did, we graphed systems manually, found the point of intersection. We're going to see how we can also use our graphing calculator to check to make sure that we get the right answer. So we want to solve the linear system graphically, then verify, and we'll verify using the calculator. So in the case of question A, those two equations are in slope-intercept form. You got positive y by itself. So for the first line, m, the slope is -2, which you write as -2 over 1, and b, the y-intercept is +2. Are you with us, Brock? Okay, heads up, please. So you got our y-intercept of +2 and our slope of -2 over 1. So we can go a rise of -2 and a run of 1, and we can do that multiple times. Or we can rise +2 and run -1. We can do that multiple times as well. All those points line up. So there's that first line. And again, our lines always have arrows on the end. The second line is in slope-intercept form as well. M, the number in front of x, would be 1. So we can write that as 1 or 1 over 1 because slope is always rise over run. And B, our y-intercept is -7. And that's where we start. Start with your y-intercept, rise 1, run 1. And you can do that multiple times. You can also rise -1 and run -1. You can do that as well. Remember, in this case, we want to find the point of intersection between the two lines. And by applying the slope 1, 2, 3 times, you actually get to the point of intersection. It is the point 3, -1, 2, 3, 4. That is the point of intersection. That is the solution to the system of equation. The solution is the point of intersection. And in this case, that is the point 3, -4. Now, here's how you can check that on your calculator. If you have a graphing calculator, you want to go to y equals, which is along the very top row, the first button in the top row. Hit that. I have some equations in there from a different class, so I'm going to hit clear to get rid of that first equation. And I'm going to input my first equation in this question, which is -2x plus 2. So you have to use the negative key, which is at the very bottom, second last column from the bottom row, -2x, 2, and then the x key is up here below the mode, x comma t comma theta comma n, that's your variable, always x, and then plus 2, enter. That puts that equation in there. I'll clear the second equation that I have in my calculator, and I will go x minus 7, enter. So I put both of those equations in there. Now, when you graph, you can change the windows, which tells you what the smallest x value and the largest x value you can see is, what the smallest and largest y values are that you can see. If you go zoom and then hit number 6 for Z standard, so zoom is in the very middle of that top row, and then choose number 6 for standard, that sets the windows between -10 and +10 on both axes. So when I hit enter now for choosing, actually I'll go number 6, I should say, presume standard, it sets my windows between -10 and +10 on the X and Y axes, and it draws both lines, which they look fairly similar to the ones that we have drawn on the page. But your calculator can also determine the point of intersection for you. So to get that, you're going to go into this calculate mode, which is above the trace key. To get calculate or anything in blue, you got to go second function first. So second function trace for calculate. And then you can see you have a choice of 7 different things. We want to do the 5th one, which is the point of intersection, the intersect. So I'll choose number 5. And now your calculator asks you to identify what 2 graphs you're going to use. And there's only 2 graphs in my calculator. So right now it says first curve question mark. Is this the first curve? Sure, that's my first curve. That's my first equation. So when I hit enter to verify that that's my first curve, notice that the cursor switches to the second curve and asks, is this your second curve? Which it is. I only have 2 graphs in my calculator. Where this is used, though, is if you have more than 2 equations in your calculator and you're trying to find the point of intersection between 2 specific equations. That's where this is really important. But if you only have 2 in there, you can just go enter once for the first curve, enter once for the second curve, and then the last thing it asks us for is a guess. Now again, there is only 1 point of intersection here, so we don't have to put anything in for the guess. Some graphs are curves, nonlinear, and a nonlinear graph and a linear graph might have more than 1 point of intersection. So this is where you would narrow down for a specific point of intersection that you're looking for. But because there's only 1 here, we don't have to change anything. We just go enter again, and then the calculator finds the point of intersection. You see at the bottom it says intersection, where x is 3, y is -4. So we just verified the point of intersection that we found manually. Okay? Now for question B, what's different is that the equations are not in slope-intercept form. So we need to put them in slope-intercept form so we can graph them. That is one option. Another option, if we wanted to, we could graph them by finding the intercepts, the x and y intercept. But I'm going to do it by putting it in slope-intercept form. I'm going to get positive y by itself. So in this case, we would do that by first subtracting 2x from both sides. And then we have to divide both sides by 3. So on the right side, you're going to have -2 over 3x minus 1 over 3. So our slope is -2/3, which is no problem. But in this case, B or Y intercept is a fraction, -1/3. So we are going to have to kind of guess where that is. We are going to kind of have to guess where that is. I'm going to use that first grid to do this one. Y-intercept of -1/3, slope of -2/3. So -1/3 is approximately right there. Approximately. Slightly below 0. Between 0 and 1, or -1, I should say, closer to 0 than it is to -1. And then from there, I need to rise -2 and run 3. So I'm going to guess. Go down 2 and run 3. Takes me about right there. Go down 2 and run 3. Takes me about right there. Go down 2 and run 3. Takes me about right there. I could also go up 2 and to the left 3. That'll work as well. Go up 2 and to the left 3. All these points will work. So I can draw a line going through all of those points. Looks like that very last point I was off just a smidge. It should have been rise 2 and run -3. It should have been that one there. So again, our graphs, our lines always have arrows on the end. So now we need to do the same thing for the second equation. Put it in slope-intercept form. So I'll keep the -4y on the left. I'll subtract 3x from both sides. That gives me the y term by itself, and then I'll divide everything by -4 to get positive y by itself. And so m, the number in front of x, is negative 3 over negative 4, which is positive. A negative divided by a negative is a positive. And our y-intercept is also positive because it's going to be negative 10 over negative 4. So that's 10 over 4 or 5 over 2 if you reduce it, which is 2.5. It's exactly 2.5. I'm going to graph this one the same color I did the last one. So the y-intercept is 2.5. 2.5 is approximately right there. And my slope is 3/4. So I'm going to rise 3, 1, 2, 3, and run 4. I'm going to rise 3, 1, 2, 3, and run 4. I can also rise negative 3, go down 1, 2, 3, and run negative 4. That works. Go down 3 and to the left 4. All those points line up. So now I can draw my line going through those points. Whoops. So that line will look something like that. And if I put my arrows on the end, it certainly looks like the point of intersection is a point where both the x and y are integers. Negative 2, 1 appears to be the point of intersection. That will be the solution to this system of equation. Negative 2, 1. And to check it, we cannot use the original equation. So we just have to kind of make sure and hope that we did the work correctly to get y by itself, because that's how the calculator is set up. Calculator is set up to input equations in the form y equals mx plus b. So as long as we did our work right to get the equation in y equals mx plus b, then we can use our calculator to check it. Now, y equals, our m value, our slope is negative 2/3. So in brackets, I'm going to go negative, you have to use a negative symbol there, 2 over 3, close the bracket. There's my negative 2/3. I put an x in there. And then minus 1/3, which I'll also put in brackets. It's all part of that one term, that one number, so the brackets keeps it all together. Hit enter, clear the second equation, and now I have to put in brackets 3 over 4. Whoops. Let me clear that all together. There you go. In brackets 3 over 4, close the bracket, x. And now in this case, because 3/4 is exactly 0.75, you could put 0.75 because 3/4 is exactly 0.75. But for the first equation, negative 2/3 is negative 0.6 repeating. You cannot put negative 0.6 in your calculator because it's not exactly negative 0.6. It's a repeating decimal, so you have to use the exact value. If you don't, you will not get the correct point of intersection. So it's negative 3/4, or positive 3/4 x, I should say, plus 5/2, which again, we could put 2.5 there because 5/2 is exactly 2.5 if we wanted to. But there's both equations in there. I graph it and find the point of intersection by going second function trace, number 5 for intersect, enter, 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 and there we've got the point negative 2, 1. And so as long as we did the work correctly to get the equations in slope-intercept form, our solution checked. All right, so we need to do the same thing for question C. Both equations need to be put in slope-intercept form. So for the first equation, I would subtract the 5x from both sides. It'll become a negative 5x on the other side. And then divide everything by 2. Negative 2, excuse me. So I'll have negative 5 over negative 2x plus 11 over negative 2. So m, our slope, negative 5 divided by negative 2 is a positive, 5 over 2. and B, our y-intercept, 11 over negative 2, is exactly negative 5.5. And I can use negative 5.5 because 11 over negative 2 gives you exactly negative 5.5. So we start there on our y-axis. 1, 2, 3, 4, 5.5 is approximately right there. And our slope is 5/2, so we can rise 5 and run 2. We can rise 5 and run 2. We can rise 5 and run 2. All those points line up. I don't think we have quite room to rise negative 5. We'll have to kind of guesstimate where that is, and run negative 2 is approximately there, and all those points line up. Right, so there's our first graph. And again, we always put arrows on the end because the line continues forever in those directions. Our second equation, x plus 3y equals 9. Again, we want to put that in slope-intercept form. We want to get positive y by itself. So we subtract the x from both sides. It becomes a negative x over on the other side. When you divide by 3, it'll be negative 1 over 3x plus 9 divided by 3, or y equals negative 1/3 x plus 3. 9 divided by 3 is exactly 3. So here our slope is negative 1/3. Our y-intercept is positive 3. And again, we start with the y-intercept. And then we rise negative 1 and run 3. Rise negative 1 and run 3. Rise negative 1 and run 3. We could rise positive 1 and run negative 3. Rise positive 1 and run negative 3. So our line goes through all those points. And our arrows are drawn on the ends of the lines. And again, we can see that our solution, our point of intersection here, appears to be at the point 1, 2, 3, 2. And we can check that by using the calculator and putting the equations that we worked out in slope-intercept form. The first one, y equals 5 over 2, which is exactly 2.5, so we can use that if we want. X minus, because 11 over negative 2 is a negative, 5.5. Again, 11 over 2 is exactly 5.5, so we can use a decimal. But for the second equation, we can't use a decimal for the slope because 1/3 is 0.3 repeating. We're going to have to use brackets and go negative 1 over 3. It's negative 1/3 in brackets x plus 3. So because negative 1/3 is a repeating decimal, we cannot use a decimal. You will not get the right answer for the point of intersection if you put it as negative 0.3. So second function trace, number 5 for intersect, enter, enter, enter. So there we got the 0.3, 2 that we found. So as long as we did our work correctly to get y by itself for the two equations, our answer is confirmed. Okay? Okay, we're going to stop there for now. What you're going to work on is page 427 to 428, questions 5, 6, and 8. I will post these solutions to Google Classroom so you can check your work. You should have been able to count that right from your graph. Where do they intersect? What is the point of intersection? Count on your graph. Okay?